I'm going to talk about rational multipliers. So basically, but in my talk, the multipliers are going to be non-commutative. And I'm going to talk about what happens when we have a non-commutative rational function and it is a multiplier on the Fock space, or when is it a multiplier on the Fock space, and what comes out of it. And of course, I'll present some application and why we were interested in that in the first place. Let me go over the moves one more time, and I'll describe the very well-known H2 of the disk and the bounded functions, analytic functions on the disk, H infinity. The H2 is the completion of the polynomial ring with respect to the inner product, which makes all the monomials orthonormal, an orthonormal basis. And you get simply this kind of a nice space, which makes m less than infinity. So what's so special about these? Well, we all know that, but it's a reproducing kernel Hilbert space, as we just saw. And the reproducing kernel is the Zego kernel. And the algebra of bounded analytic functions is completely isometrically isomorphic to the algebra of multipliers, as we saw in Michael's talk and John's talk, to the algebra of multipliers on this H2 space. The multipliers being the functions that actually, if we multiply an element of H2, the functions on the disks, we stay at H2. And this map is just given by sending a function to the operator of multiplication by this function. And a function f is an isometry if mf so we call function f inner if it's mf is an isometry, and outer if this multiplication operator has dense range. And an inner function comes in two flavors sometimes, but mostly product of the two, but there are special cases. So it's singular if it's pointwise invertible on the disk, and Blaschke if it has this kind of a weird form, but basically it means it has zeros. And the classical result says that every function in H infinity, in fact in H1, has this decomposition as a product of a Blaschke factor, single factor, and an outer factor, which it's unique up to rescaling everybody by some unimodular constants. And basically that's it. Now, what is this? So the first piece of this is the inner part. It's the product of the Blaschke and the singular. This is the inner part of the expression. And the Blaschke part knows the zeros of f, and the singular part adds something which is a little bit less explicit, and this is somehow more operator theoretic rather than just a function which just the zeros. But I want to focus on the very simple functions, namely polynomials. So what happens to polynomials? If I take just the polynomial z minus lambda, then, well, three things can happen. Either the absolute value of lambda is greater than 1, then it's just invertible inside our algebra, and so it's definitely outer because the range is everything. If lambda is 1, then the image is dense. It's not everything, but it's still an outer function. And if the absolute value of lambda is less than 1, then this function has a 0, and we have a concrete Blaschke product and outer part of this polynomial. But the thing is that the inner part doesn't appear. And if we use the fundamental theorem of algebra, we can decompose our polynomial to product of factors of this form, and we precisely know what happens. So they are either outer or inner. And the inner part is always rational. And the outer part is always a polynomial of degree, at most the degree of f, might be less. So, and if we start with a rational function, which is bounded, then in fact, it is analytic in a slightly bigger disk. So it belongs to a smaller algebra inside H infinity, which is the disk algebra. And on the other hand, if you start with an inner, which is in the disk algebra, then it is automatically Blaschke inner. So there are no singular inners inside the disk algebra. It's not to say that the disk algebra elements don't have singular factors. That's not true. There are examples of functions which are in AD but have singular factors, but not rational functions. Okay, now I would like to take all this theory and move it to the non-commutative setting. So what can we say? So this already has, so this part of the talk will slightly overlap with Rob's talk a couple of days ago, where he presented, so the notations will be similar, but I will recall them nonetheless. So we start with the free monoid on D letters. And I replace my polynomial ring with the free algebra, which is the monoid algebra of this free monoid. And for each alpha, I have these monomials. So each monomial for me is an expression which is this product. Z to the alpha is just the product of whatever alpha describes to take. And if alpha is the empty word, this is 1. And the length of alpha in this case is just the number of letters which appear in alpha, and that's allocated by absolute value of lambda. So, and just like in the classical case, we define an inner product on this free algebra, making the monomials an orthonormal basis. And the Fock space, it turns out to be the Fock space, is just the closure of the free algebra with respect to this norm, with this topology. And Popescu rather early realized that every function f is in fact an NC analytic function on the row ball or the NC ball. It's basically the collection of row contractions of all sizes. Now I'm being a bit vague here on purpose, and I'll explain what. So in most cases, when you talk about non-commutative functions, you will see that in general, the n is considered to be finite. However, as we saw in Matt's talk, for example, on Monday, it is very useful and sometimes even necessary to let n take infinite values. For example, in Matt's talk, the reason was because we want to find the boundary which might not live on finite levels. Like for example, in this case, this is a matrix. This is a non-commutative convex set, and its boundary lives on the infinite level. But since I'm doing more holomorphic things here, this might not apply. But still, even for our result that I will present in a second, and Rob has presented before about Blaschke singular outer decomposition in this setting, the infinite level is a must for us. We don't know how to do it without it. Okay, it can be done for polynomials without the infinite level, but we don't even know if it works for rational functions yet. Okay, so generally, when I'll talk about the n will be at first infinite, but I will say at what point it will only take finite values, and we don't need the infinite value anymore. So what kind of function is this f inside the Fock space? It's the so-called non-commutative function. It's a function which takes a d-tuple of, say, n by n row contraction and maps it into a matrix, but in a very funny way. So the direct sum of two matrices is just writing, or d-tuples of matrices, just writing them coordinate-wise on the diagonal. That's the direct sum for me. And my function has to respect two things. It has to respect these direct sums, so it takes direct sums to direct sums, and it has to respect, well, similarities in a relative sense. Namely, if something, this should be the other side. It's just, so if something is in the ball and there is an element of GLN such that coordinate-wise similarity will preserve it in the ball. Let's keep it in the ball. And F just behaves like an equivariant function. In fact, each non-commutative function extends to the so-called similarity envelope of non-commutative set. We basically, if in our case, if we take the ball, it's just all the tuples which are similar in this sense to strict row contraction. It has a nice description I will discuss in a second. And in this case, F is just equivariant, simply with respect to this action. So in general, these functions, they need not be analytic, but there is a mild conditions that make them analytic. For example, a certain flavor of local boundedness. These functions somehow arose independently in many ways from different directions. In Taylor's work, in Takesaki's work, and in Voiculescu's work. And these axioms are somehow up to shift. If you want to make it continuous, you just assume unitary equivariance, for example. It's a very natural set of axioms. And this kind of local boundedness condition ensures already automatically analyticity. But I'm not going to assume that, because in fact, I'm going to mostly talk about bounded functions. Now, if you ask me why functions in the Fock space, which are not necessarily bounded, are still analytic, it's just because if you take a function f in the Fock space and you just replace it by f r z, then this function is already bounded. So slightly shrink the argument for some r between 0 and 1, and this function is bounded, so they are all analytic. And but moreover, so this analogy continues with the fact that the Fock space is a non-commutative reproducing kernel Hilbert space in the sense of ball marks and Binnikov with these kernel functions. Now, let me just jump a bit forward. So H infinity of the ball is precisely the left multipliers of the Fock space, completely isometrically. And it's the free semigroup algebra studied by Davidson and Pitts. So this algebra was successfully studied by Popescu, Davidson, Pitts, and others. And the map is, again, you just send it to multiplication operator, but this time on the left, and direction matters because we are no longer commutative. And the definitions are the same. So non-commutative function is inner if the multiplication operator is an isometry, and outer if it has dense range. Now, if we want to talk about zeros, there are various ways to do that, and we choose one. We talk about the singularity set, which is basically directional zeros. So to each f, we associate all the points in the ball in which f is not only singular, but we also associate the direction of singularity. And with this association, the Popescu-Davidson-Pitts Berlin theorem allows us to produce a right invariant subspace of the Fock space, and thus an isometry, which has this subspace as an image. And the theorem is that, well, in fact, this is not a row isometry, but it's single isometry, and each function admits this kind of decomposition, with B being a Blaschke, which means that this space is just the image of this isometry, and then a singular, and then an outer. Okay, and that's a nice result. But if I call something Blaschke, I would like to know that it has some kind of, but before that question, it has some kind of nice properties like in the classical case. So that's what I'm going to describe next in the remaining time. Just a short question. This entire description in the classical case can be given completely in function theoretic terms, but we don't have any NC function theoretic description of inners or Blaschke inners. That would be very interesting to know in my opinion. So now, what is the outer factor of a polynomial? So let me just go a bit faster. The outer factor of a polynomial is just a polynomial. And you can see it by looking for a second at this kernel function and realizing if you take the point to be jointly nilpotent, then you get a polynomial. And conversely, if you start with a polynomial, you get a kernel function. So the outer factor of a polynomial, just as in the classical case, is a polynomial of degree, at most a degree of f. So the inner factor is rational, but the question is whether it's Blaschke. So first we had this result. We didn't know this, but we knew that just like classically, if you started with something in the norm closure, in the supremum norm closure of the polynomials inside the bounded non-commutative functions on the ball, then, and this function is an inner, then it is Blaschke. So basically the question is whether a rational function, non-commutative rational function, belongs to this algebra. Well, two ingredients, realizations and the Popescu's joint spectral radius. Now, I don't want to go into the details because I'm short a bit on time. So let me just say what a realization is. So for non-commutative rational function, one can write this kind of an expression with B and C vectors and A's matrices, and this is called the descriptor realization of F. And the thing is that these type of realizations capture the domain of the function. So basically wherever the function is defined. Now, a non-commutative rational function, you can imagine slightly more complicated than the classical one, but it's precisely what you think. You take some expressions in polynomials, then it puts some inverses in, and as long as this is defined at some matrix point, you're fine. That's a valid rational function. So realizations are a very important tool, and as we saw this morning in Serban's talk, they appear in free probability and other places like free real algebraic geometry and non-commutative algebra. But now if you combine these two ingredients of the spectral radius and the joint spectral radius and this realization, you get the following theorem. So if you start with non-commutative rational function with 0 in its domain, and of course if 0 is not in its domain, it cannot be defined on the ball. So then it's in the Fock space if and only if it's a bounded function, if and only if it's actually in the disk algebra, if and only if it's actually defined and analytic on a slightly bigger maybe ball around the origin. Right? So a ball of radius not 1, but some r for r greater than 1. And all these conditions actually, well, the proof actually entails the fact that every NC rational function is a sort of a kernel function. So now, what can be said, what can we deduce from this? First of all, since every non-commutative rational function is in AD, so its inner factor is Blaschke. A polynomial is outer if and only if its singularity set is empty, just like in the classical case, so it has no zeros. But moreover, you can say something like that. So if you start with non-commutative rational function, the spectrum of the associated multiplier, left multiplier, is basically the closure of the spectra of its values. And that's something I'd like to know whether it's true for every multiplier on the ball. And note that here, for example, we don't need the infinite value, but only finite ones. Now, moreover, this result tells us that if you consider the spectral map, so the map that sends every operator to its spectrum as a compact subset of C, then for every non-commutative rational function, the associated multiplier is a point of continuity of the spectrum. And this follows from a result of Conway and Morel combined with some results of Davidson and Pitts, and this result above about the spectrum of a rational multiplier. So if I won't go into the proof of this because I'm out of time. So just a brief summary. The Blaschke singularity decomposition extends to the non-commutative setting in a very nice way. And moreover, the inner factor of every non-commutative rational function is Blaschke. And this decomposition sheds light on the spectral properties of the operators LF. But there are still quite a few open questions that I'd like to have an answer to. So thank you.